resistant bacteria. The version.
Assalamualaikum and very good morning. I greet to everyone. My name is Arash Zulkarnain. I'm from Institute of Bioengineering and Nanoelectronics. So my presentation today is about dielectrophoretic rapid characterization of antimicrobial resistant bacteria, Escherichia Coli, same as what my colleague Akmal just presented just now. Next slide. So what is E. coli or Escherichia coli actually? E. coli is a gram-negative bacteria. It's a rod-shaped bacteria commonly found in environment. And when I say environment, it means soil, water, even on our skin and stuff. And it's one part of normal flora in one part of bacteria in normal flora, which is in our digestive system, and it could cause minor and severe illness for humans. Sounds really simple, right? But why does everyone do research about bacteria itself? Next slide. So, as you can see in this slide, what's the difference between picture on the left and picture on the right? This is E. coli. Next. Actually, the difference is antibiotic profile of the E. coli itself. The left side is susceptible and the right side is resistant E. coli. So by microscope, there's no difference between these both antibiotic profile of E. coli. Really minimal properties difference, looks almost the same, rod shape also under microscope. Next. So E. coli make part of a few components, same as almost bacteria, which is outer wall, cell membrane, cytoplasm, DNA, and flagella. Next. So what is the problem actually when it comes to bacteria? Because bacteria cause a highest number of infection towards human all around the world. So right now, by E. coli, by bacteria itself, over 2.17 million deaths all over the world caused by infection of E. coli. E. coli is actually one of the highest bacteria that cause infection and also mortality for the people that cause infection by it. Why? Because when it comes to infection, no matter what, COVID, bacteria, or any virus or bacteria, is actually prominent depend on how long the infection resides in your body. So how do we solve the infection itself? We have to take a look on the detection of the bacteria itself, which is conversion method. Actually, conversion method still used in the lab nowadays, which is to grow the bacteria itself use 24 hours, and to check the antibiotic profile itself use another more 24 hours, which is total of 48 hours just to check the antibiotic profile of the bacteria. Next. So this is a current biosensor device. We have culture antibiotic susceptibility test, which is our current in our lab, not only around Malaysia, but actually around the world as well, which is portable, cheap and simple, specific detection. The disadvantage is 1 to 5 days processing time. Then we understood that the infection that caused death itself have really depend on the conventional technique. And the sensitivity also 60.2%. And nowadays current biosensor is nuclear imaging, high sensitivity, rapid detection by 1 hour processing time, PCR, sensitive and specific, higher sensitivity also, long processing time, unfortunately, and complex, and really need a professional skill to use PCR. And then magnetic resonance, which is automated, not portable, expensive, and market tagging, which is sensitivity 95% next. So, as been explained by the dielectrophoresis by my colleague just now, so dielectrophoresis is a technique that uses non-uniform electric field that consists of 3 main components, which is particle, medium, and frequency itself. Next. So dielectrophoresis, based on what I explained just now, particle, medium, and frequency really a main point for dielectrophoresis. By introducing particles such as biology particles with constant medium, we could actually do on different frequency the application on separation, manipulation, and characterization, which is rapid, sensitive, non-label, and contactless. Next. So this is our comparison method between the conventional technique and versus DEP, which is conventional more 24 hours, our DEP is real-time detection, but as I said, the sensitivity really low nowadays on susceptibility testing, and our DEP is sensitive, but required acidophile joule heating still a problem in past DEP research and electrolysis as well. Next. So this is our method. First one, we have to find the physical properties of E. coli. My colleague just now focused on the one on the velocity, which is experimental, but mine is much focused on theoretical and experimental. We verified our theoretical with experimental. Next. So when it comes to theoretical, we have to find the parameters of the bacteria based on cell wall, based on cell membrane, and based on cytoplasm. We could find the conductivity, thickness, and permittivity of the bacteria, which is contribute to the polarization, which is called Clausius-Monserrat factor, which contribute to the polarization of the bacteria itself. Next. So this is our reference on base past DEP research. As you can see, it's not consistent when it comes to dielectrophoresis. Different inter-electron gap, different voltage, different frequency, different sample obviously because we need to test every bacteria. Size sample different and different medium. So as I said, three main components just now actually depend on the DEP itself. So we have to find the biological particles of this bacteria. We need to constant on the medium and also the inter-electron gap, which is doesn't give effect on the DEP response, but give effect on the electric field of the every experiment. So on this base past DEP research, we decided to use DI water, which is easily accessible, can be used for every biological particle. Dilution factor of distilled water can be applied to any sample. Next. So we fabricate our device, which is we use lift-off process, and then we use gold. Next. And then this is the microelectrode gap that we fabricate, which is 20 micrometer. That is the FISAM. And that's the overview under microscope. And this is our procedure methodology of our DEP itself. Next. So this is our MyDEP simulation. We explain that polarization factor of E. coli is based on the most outside, which is cell wall first, go to the inside, which is cell membrane, and go to the inside, which is cytoplasm. And during MyDEP simulation, we got 0.47 MHz, which is explained no movement of particle. Next. So this is the DEP response, which is negative depth, move away from the high electric field, which is edge of electrode, crossover frequency, no movement of particle, and P depth, move to the edge of a particle. Next. So when on crossover frequency, there is no movement of particle on 0.47 MHz, P depth and N depth or 0.47 MHz if it's not crossover frequency. Next. So this is susceptible E. coli. We verified our simulation by using susceptible E. coli on 0.47 MHz, and what we got the response is crossover frequency on 0.47 MHz for susceptible E. coli. And for resistant E. coli, 0.47 MHz got positive dielectrophoretic forces, which is on edge of electron. Why is this? Because why we got different response actually for different, because of different minimal properties. Next. So susceptible and resistant, although the diameter of E. coli is almost the same, thickness of cell membrane is the same, but thickness of cell wall, there's slightly minimal different properties on the thickness of cell wall. Next. So we conclude that the susceptible is 80 nanometer in terms of cell wall, and resistant is 20 nanometer in terms of cell wall, which contribute to the conductivity of the cell wall itself, because much thicker the cell wall contain more charges of the bacteria and also contain higher conductivity. Next. So we have susceptible real, which is our susceptible. has the same crossover frequency, which is 0.47 megahertz. But on 0.47 megahertz, our resistant E. coli show MyDEP response, which is because of higher conductivity, cause higher polarization on the cell wall itself, cause different response of resistant compared to susceptible E. coli. Next. So minimal bacterial difference can be observed on rapid characterization using DEP. The DEP crossover is a stable technique to develop an accurate DEP device for characterization, which is we would like to, in a further way, we would like to improve a stable baseline for every each bacteria, thus integration for our system, for our technique. That's all for me. Thank you.
Okay, thank you very much, Mr. Arash, for a very nice presentation. So now I open the floor for any question. Anyone?
Thank you. Nice presentation, Arash. You said just now that there are 3 parameters that have to remain constant, the medium and the other 2 I don't remember, but how would you decide and choose these parameters? For example, I think the micro electrode gap was 20 microns. So how did you arrive there?
Okay. So first, the parameters that based on the EP research before this, it used different mediums has a lot of different conductivity and permittivity. That's why when we play with sample, for example, sample bacteria or sample virus, it uses a lot of different medium with different conductivity and permittivity. By constanting the dilution factor using one medium that is constant, which is the water, which is actually accessible and easily to dilute all other medium that when it comes to bacteria or virus, we could actually provide focus utilization of polarization only on the biological particle itself. So every medium that used by this biological particle can be diluted using the same medium, which is the water, based on the past research also. When it comes to inter-electrode gap, it doesn't change any DEP response, but it actually contributes to the electric field of the device itself. When it comes to electric field of the device itself, we would like the highest electric field with the highest DEP force. So to maintain on the lower voltage peak to peak, which is easier to accessible and easier to experimental, we choosing the best inter-electrode gap, which is 20 micrometer, based on the before past research dielectrophoresis.
Okay, thank you very much, Mr. Aras. I have one question. Sorry. About the mechanism to detect the E. coli. So you showed us now on the nuclear method.
Yeah, one of the current biosensor method.
So is it a typo error or because under this advantage, the time for detection is 1 hour?
Actually, time for detection is actually really rapid actually for nuclear imaging.
So that was a disadvantage.
But the nuclear imaging technique for the processing of the sample preparation, we try to include every sample preparation in our for our technique. Because for example, nuclear imaging sample preparation actually for now for the past research, it's not stable, it's not constant, but it's from this amount of time until the maximum that I watch is at least 1 hour for the detection, for the processing sample.
Okay, alright. Okay, thank you very much.